This is Danny Tang. I'm doing the probability and stochastic processes homework number 10, problem 1. Problem 1 gives us a Poisson process that's defined by several properties, and it says that the number of points n, t1, t2 is a Poisson random variable with parameter lambda times t. So you treat lambda t as one entity, and this is the equation for the Poisson random variable. And it's really similar to just the Poisson distribution, except that instead of just lambda, this is lambda t. So this equation is pretty much the same, except you have an extra t. It says that intervals are non-overlapping, then you can define the two variables as independent, and that the Poisson process is an independent increment process. So for part A, they want you to find expected value of x of t. And to find this, we'll do it pretty much the same way that you would do find the expected value of the Poisson variable. So in Poisson, we know that expected value of x is just lambda. So you take the derivative of this, you move the e of negative lambda to the left side, so it's just e to lambda. And then you take the derivative with respect to lambda. And so this brings down a k on the right side. And then you just rearrange this so that lambda is on the left, and then you have e of negative lambda on the right side. And so this expression is the expected value, and you know that left side is lambda, so lambda is the expected value. So similarly, we use the equation given to us in the problem here, and we do the same thing, except this time we take the derivative with respect to lambda t, and so you pretty much get the same thing. You bring out a k here, and we rearrange the equation so that e of lambda t is on the right side, so it becomes e of negative lambda t, and then lambda t is on the left side, so, and this is the expected and this is the expected value expression. So you know that expected value of the process x of t, Poisson process x of t, is just lambda times t. So part B asks us to find the autocorrelation of this process. So this is the expected value of xt1, xt2 is just the definition, and you can rewrite xt1, xt2 as this expression here. It's kind of just the same thing, but you write it a different way. So tx1 times the parentheses xt1 plus xt2 minus xt1, and then you just put this into the expected value and distribute out, and you get expected value of x squared t1 plus expected value of xt1 times expected value of xt2 minus xt1. So then, using what we found out in part A for expected value of a Poisson process, you just put in the lambda t1 wherever you see xt1. Well, x squared of t1 is actually just 1 plus lambda t1 times lambda t1, because it's the same, it's a similar expected value as just a random variable. So when you put in, you basically just distribute out here, because these are not squares. You just put lambda t1 and then lambda t2 here, lambda t1 here. So then you see that lambda squared, t1 squared, and this lambda squared, t1 squared cancel out. So then you're just left with this expression here, lambda t1 times 1 plus lambda t2. And this is for the case where t2 is greater than t1. And for t1 greater than t2, it's the same process as here, except you switch out the variable t1 here for t2 and t1 here for t2. So you just have two different parts for when T1 is less than T2 or for T2 is less than T1.